Good afternoon, everyone. Welcome to the Tutte Colloquium for today. I'm happy to introduce Douglas Stebila, who's a professor in our department and who researches cryptography. Please, the floor is yours.
Okay, thanks. Hi, everyone. Thanks, Sam, for inviting me. So today I'm going to talk about some work in post-quantum cryptography about using a transform called the Fujisaki-Okamoto transform that plays a key role in post-quantum cryptography, and we're going to see how to use it to kind of extend and add functionality to cryptosystems. So this is based on a series of papers with a few different co-authors, including Louis Glabush, who was a master's student here in the department, Felix Günther, Britta Hale, Catherine Hollemans, and Elizabeth Van Oorst, who was a URA here in the department last summer. All right, so let me motivate this off with some attacks. Okay, so we're going to start off by looking at public key encryption. All right, so public key encryption, we have two parties, Alice and Bob. Alice generates a key pair, a public key and a secret key. She publishes her public key, and then anyone can send a message to Alice by encrypting a message under Alice's public key. And then she should be able to decrypt that ciphertext using her secret key, but no one else should be able to do that. So this allows Bob or anyone to send a confidential message to Alice. And we highlight this as kind of one of the most important things in cryptography. Okay? But that's actually a bit of a lie. No one uses public key encryption. Okay? Because we don't actually want to send long messages using public key encryption. Okay? What we do instead is we encrypt our application data with a symmetric encryption scheme, which is much faster. A symmetric encryption scheme where Alice and Bob share a secret key. To get that shared secret key, we do use asymmetric or public key techniques, but use something that's in a slightly different shape called a key encapsulation mechanism. Okay? But let me show you kind of a sample of that, something called the Diffie-Hellman key exchange protocol, my favorite protocol in all of cryptography. So we have two parties, Alice and Bob, and their goal here is to establish a shared secret using only public communication. Okay? So we'll work in a group with a generator, little g, of order q. And Alice will pick an exponent a and compute g to the a, and send that to Bob. Bob will pick an exponent b, send the public value g to the b to Alice, and they can compute a shared value g to the ab. Okay? And neither of these values was neither of the secret values, little a or little b, were transmitted, but at the end they can still establish a shared value between them. Okay, and hopefully this value is secret. Now we're going to look at a generalization of this called a key encapsulation mechanism. Okay? So kind of same pattern, but we'll just give abstract names to the operations. Okay? So Alice will generate a key pair, a public key and a secret key, and she'll transmit that public key to Bob. And then Bob, to respond to her, will run what's called an encapsulation algorithm, where his encapsulation algorithm will produce two things. A cipher value that he can send to Alice over the public channel, and his copy of what will be their shared secret. Okay. Then Alice, when she receives the ciphertext value from Bob, she runs a corresponding decapsulation algorithm with her secret key, and she recovers K, the same shared secret that Bob computed on his side. All right, so this is kind of the shape of the object we like to work with. We don't actually need to control what the key K is going to be between Alice and Bob. We just want it to be a random key. And once we have a good random key, then we can use that in a symmetric encryption scheme to encrypt whatever we want. And we do this for performance reasons. All right. Okay, so this chem structure is kind of really at the heart of everything we do in post-quantum cryptography. Okay? So all of the post-quantum encryption standards that we've been developing are in the form of chems, key encapsulation mechanisms. So there's several standardized chem algorithms so far. The US government standardized an algorithm called ML-Chem, which was co-authored by a UW PhD student, John Skank. They've selected another one for standardization that they're still kind of finalizing the details on. And a third algorithm, PhotoChem, has been, didn't make it through the NIST selection process, but has been standardized by ISO. And I was involved in that here on UW's behalf. Okay. Right. And these algorithms are already starting to be fairly widely adopted. So in major communications protocols, like the transport layer security protocol that your web browser uses, in secure messaging protocols like Signal or iMessage, these are already all using MLChem. Okay, so if you're chatting with your friends, your chats are already post-quantum encrypted. Okay, and half of the web traffic that we do already is already post-quantum encrypted. Okay. All right. So chems are really this fundamental object that we want for post-quantum secure cryptography. Okay. And all of these chems are built by first preparing a public key encryption scheme, and then transforming that public key encryption scheme into a chem via something called the Fujisaki-Okamoto transform. What this transform does is it transforms, as I said, from a public key encryption scheme to a key encapsulation mechanism, but it also upgrades the security as it does this. So we start off with a public key encryption scheme that has a relatively weak level of security, and then it upgrades it to have stronger levels of security. Right. All right, so let me kind of tell you what it means for these schemes to be secure and what the difference is between weak and strong security. Okay. So a chem, in order to be secure, it should have the property that the key that it establishes between the two parties is indistinguishable from a random string, okay? Even to an adversary who observes all the communications that goes back and forth between the two parties. Okay? So indistinguishability from randomness, that's the fundamental security property of a key encapsulation mechanism. Okay? So the way we model this is with a game played between a challenger and an adversary. So the challenger will set everything up. The challenger will first generate a key pair using the key generation algorithm and prepare the encapsulation of a random key K0 under the public key. Okay. But then to challenge the adversary to distinguish that real key K0 from random, the challenger will also pick a random key K1 from the key space, so maybe a random bit string. Okay. And then the challenger will flip a coin. Okay? If the coin comes up 0, then the challenger will present to the adversary the public key, the ciphertext, and the real key, K0, that was derived by this encapsulation process. Whereas if the coin comes up B equals 1, then the challenger will give the adversary the random key, K1. And the adversary's task will be to figure out what actually happened. Did they get the real key, or did they get the random key? Can they guess the hidden bit B? If they can, then they're able to distinguish real keys from random, and that means that our keys weren't actually very good. They weren't indistinguishable from random. Okay. Right. And so we're going to measure the adversary's advantage in being able to guess the hidden bit B. Okay. Of course, they can guess it with probability 1/2 just by flipping a coin, so we'll measure how much better they can do compared to 1/2. Right. And we'll say that a key encapsulation mechanism is called in CPA secure if this advantage is small. Int here stands for indistinguishability, and CPA here stands for chosen plain text attacks, which is kind of a little bit of a misnomer in this case, but it's a historical term. It basically means the adversary just gets to be passive. Okay? All right, please feel free to ask questions as we're going along. So if you do have any questions now or as we go, please feel free. All right, so this is our base level of security for a key encapsulation mechanism, but it is only secure against a passive adversary. We want to imagine an adversary who can also interact with the system, an active adversary. This is where chosen ciphertext attacks come in. Because real attackers don't just eavesdrop, they do kind of modify or interact with the real parties. They do send messages on the network to try to probe and break into a system. Okay? So we're going to want to be secure against an adversary who does that. And the way we're going to model an active adversary is we're going to give them the power to have some of their own ciphertexts decapsulated. So maybe they can learn what the secret key is, the shared secret that's for other ciphertexts, and then their task is just still try to break the particular one between Alice and Bob. So the difference in this experiment is in these two red lines here. So our adversary is going to be given their challenge to break, And they'll also be given the power to request to have ciphertexts decapsulated. Okay? That'll allow them to perhaps gain more information, modeling them being an active participant in the protocol. We have to impose the condition that they can't ask for the challenge ciphertext to be decapsulated. That would make it too easy. But other than that, they're allowed to make these queries and try to use this to learn information about the system and then eventually get their guess of what the hidden bit is. Right. So this is called indistinguishability against chosen ciphertext attacks. Right. Okay. And maybe one thing to highlight here, this will be a prelude to stuff that comes later, is that we're giving the adversary exactly one challenge ciphertext to break here. Okay? So we generate one key pair and one challenge ciphertext, and we ask them to see if they can break that with the help of this decapsulation oracle. Okay. All right. But it turns out that this is not necessarily reflective of the security properties we would want if a key encapsulation mechanism is deployed in practice. Okay. So I'm going to show you two attacks that motivate the two pieces, the two lines of work that I'm going to talk about today. Okay. So let's imagine we have a client server set up, a web server and a bunch of web browsers. Okay. And this web server is going to perhaps use the same public key for its entire lifetime, but it'll have many clients connecting to it. Okay. So what will happen is these many clients will encapsulate against the server's public key, producing each their own ciphertext for the count. Okay. And perhaps our adversary's goal is just to break one of these. They may not care particularly which one they break, but they just want to successfully break into some client session with the server. Okay? So this is now a multi-instance problem. Okay? So the adversary observes many ciphertexts, and their task is to break one of them. Right? That's not covered by the definition we had on the previous slide, because there's only one challenge ciphertext. Okay? All right, so let's see how this turns into an attack against a chem construction using this FO transform. I haven't told you much about this FO transform yet, but one of the key things that happens inside the FO transform is that it de-randomizes the encryption process. Okay. So normally we think of encryption, public key encryption, as a random process. It samples some randomness that it uses to construct a fresh encryption. But in this FO transform, it actually de-randomizes it. Okay? So it's going to kind of have a message M that it transmits, which is kind of the shared key that we're going to get at the end, or a seed for that. And it's going to use, as the randomness in the encryption algorithm, a hash of this message. Okay? So this semicolon here denotes, what comes after it is the randomness for this probabilistic algorithm. So we've de-randomized this probabilistic algorithm. Okay. Right? And so that means that this function is overall a deterministic function now. And in particular, ciphertexts produced using this algorithm are deterministic functions of the message once the public key is fixed. Okay? That means that any adversary who has the public key can recompute what the exact ciphertext would be for any particular message. And so if the message space is not too big, the adversary can go through all the messages, produce all the corresponding deterministic ciphertexts, and perhaps gain some information that way. Okay. And so to give you a visualization of this, let's imagine we have our message space here. Okay. And a bunch of challenge ciphertexts are observed from the many clients interacting with the server. Okay. And then the adversary, perhaps in a pre-computation attack or just through any kind of attack, picks a bunch of random messages and encrypts those. Okay? And it may so happen that one of the messages that the adversary picks produces a ciphertext that matches one of the ciphertexts they observed from the honest parties. Now, because encryption here is deterministic, then two ciphertexts being equal means that the two messages underneath were equal as well. And so the adversary, in having picked the message for this, learns what the message behind the challenge ciphertext was. Okay. All right, any questions so far? Yeah.
So how do we know that encryption is one-to-one?
How do you know decryption is one-to-one? So we'll actually, that is a good question. So as we go through some details a little bit later, we'll come to a property called rigidity that covers that. Okay. All right. So we can kind of count the success probability of the adversary for this type of collision finding attack. So if the number of challenge ciphertexts is little nc, and the number of ciphertexts produced by the adversary during their attack is capital N, and we've got our size of the message space here, then we're just really looking for a collision attack, and it'll scale roughly as this. And if you plug in numbers from some of these standardized algorithms, then we start to run into a problem. Okay? So the message space in, say, the Photochem standard is 128 bits long. Okay? And if you take 2 to the 64 challenge ciphertexts, and the adversary does 2 to the 64 encryptions themselves, then with high success probability, it will be the case that one of the adversary's encryptions matches one of the challenge ciphertexts, and they will recover the secret key for this challenge. Okay. So in this multi-ciphertext setting, where the adversary gets many challenges, at this kind of trade-off of number of challenges versus adversary work, we have high success probability. Okay. And what that means then is that in the multi-ciphertext scenario, the security of this encryption scheme does not meet the 128-bit target. Okay? It really only effectively is secure against an adversary who does 2 to the 64 work. Okay? And now this is, on the one hand, suboptimal. It's not technically a break of these systems against their claimed security properties, because they only claimed single challenge security, which is all that was demanded in these standards competitions. Okay? But nonetheless, it would still be nice for these to have multi-challenge security. Okay, so we'll look at that in one part of the talk. The other attack I want to mention is if we follow further on into the FO transform, we'll see another step that goes on. Okay? So I've mentioned already, after we've done this de-randomization, basically every message corresponds to exactly one ciphertext. So as a way of enhancing the security of the system, the FO transform, when you're decrypting, doesn't just decrypt the message, it then does a re-encryption process to check and see if the message that I've decrypted re-encrypts to the ciphertext I received. Okay. So what goes on is that if we receive a ciphertext, we decrypt it to recover candidate M prime, and then we re-encrypt that M prime using this de-randomized encryption process. Because it's been de-randomized, it should re-encrypt to the same ciphertext, so we'll check and see whether it does. If it does, then we will accept that. We'll accept that this is a valid encryption, and we'll output a key derived from the message in the ciphertext as our shared secret. If this check fails, then we'll reject, because something funky is going on. Okay. All right. And the idea here is that if the ciphertext was well formed, if it satisfies this check here, then that means that the adversary kind of knew the message. They must have formed the ciphertext by following the process, so they knew the message. And in the chosen ciphertext attack scenario, if we give them a decryption oracle, then that doesn't really help them, because we're only giving them answers that they already knew themselves. And so that's what basically upgrades from passive security to active security. This re-encryption check makes sure that the adversary knew the answer already, and hence we're not giving them any new information. All right, this is great. This is kind of a key part of the Fujisaki-Okamoto transform, but unfortunately, it is kind of a bit fragile. Okay? It really depends on doing this re-encryption and doing this check. And it might be the case that if you skip that check, something goes wrong. Okay? In particular, you basically are degrading back to this more passive form of security, but still allowing active interactions with the adversary. And if the adversary sends a malformed ciphertext, then indeed they might learn something that they can take advantage of. Okay. All right. And this is not a hypothetical condition. So the HQC scheme, one of the algorithms that has been selected for standardization, its reference implementation had a bug that skipped this re-encryption check. And no one noticed this for 19 months. Okay? Even though this is kind of one of the most highly scrutinized algorithms on the planet for this 2-year period. Right? And one of the reasons that no one noticed this bug is that it doesn't show up in normal testing. Okay? All of the basic correctness tests that you might run between 2 implementations still passed. Okay? All right. I'll talk about the bug a little bit later, but basically there were 2 bugs in the software that kind of interacted in a peculiar way that basically made it so that the check got ignored. Okay? Someone was trying to be very clever in one part of the source code, and they failed in being correct there. But they also made a mistake somewhere else, and those 2 things kind of canceled each other out, and both honest and bad ciphertexts successfully decapsulated. Right. And this is actually not a new pattern in vulnerabilities in cryptographic implementations. There's a famous bug about a decade ago that came to be called go-to-fail because this was in a piece of Apple source code, and they were kind of checking a bunch of conditions, and someone had copied and pasted a go-to line, like it said, if something go-to-fail, and they copied and pasted another go-to-fail line right under that. So the second one always got executed, even if the if condition was false. And so it resulted in subsequent checks being skipped. Okay? And this also went unnoticed for several years. Okay? So the overall lesson we can take from these 2 patterns is that there is a danger when there are security critical steps that might get skipped. And skipping these steps doesn't show up in your routine testing. All right, so those are our 2 motivating attacks. So let me put all this kind of together into one picture. Okay, so this first attack we saw was about multi-challenge collisions. Okay? And this arose because there's a gap between what we originally asked for, single challenge security, and where we might use this in deployment, multi-challenge settings. The second attack was about a skipped re-encryption check. And this occurred because of a gap between what you might do in an implementation in terms of whether or not all of the critical steps actually affect correctness of the implementation or are visible in the testing. And so I'm going to show you 2 techniques that we've kind of developed to try to detect these types of to try to add protections for these types of issues. Both of them involve enhancing this transform that constructs a chem from a public key encryption scheme. So we'll tweak this transform in different ways in order to add protections against these types of attacks.
Is the multi-challenge collision, I'm not sure what model you're using for that. Like, is it accelerated by a quantum computer or not? Because it maybe depends on how things are stored in terms of the...
Right. So is the multi-challenge collision attack accelerated by a quantum computer? So this is all classical analysis that I'm talking about, right? So I mean, you get this kind of square root effect on the security level, but that square root is coming from a birthday paradox.
No, I understand, but if you had a quantum computer searching for collision.
If you had a quantum computer searching for collision, would it be even worse? Possibly. So I think it would. Yeah, so I mean, we haven't done a quantum analysis of this. I guess you'd be looking at storing a fairly large amount of quantum information to hit the right part of the trade-off. I don't remember whether this would be like, because there's like the square root and then there's the 1/3 collision finding attack. I'm not sure of how this would come out there. But you'd still be talking about like storage around 2 to the 40 to 2 to the 60. Right. Okay, any other questions as we go? Okay, so the plan for the rest of the time, I'll tell you a little bit more in detail about the FO transform. We'll look at these 2 themes and then wrap up. Okay, So this FO transform, I've already given you the main idea. It takes a passively secure public key encryption scheme and upgrades it to an actively secure key encapsulation mechanism. Okay. And the modern way of viewing this transform is to decompose it into two subtransforms called the T transform and the U transform. Okay. And what the T transform is going to do is it's going to take the randomized public key encryption scheme and it's going to do the de-randomization and the re-encryption check. Okay. And that'll make a deterministic public key encryption scheme with a couple of extra characteristics. It'll have a property called rigidity, and we'll talk a little bit later about what the security level or the security definition for this scheme actually is. And then we'll apply a second transform, the U transform, which will take this public key encryption scheme and convert it into a key encapsulation mechanism. All right, so let's look at the T transform. Okay. So like I said, it does de-randomization plus a re-encryption check. So this de-randomization is exactly what we saw before. It will encrypt the message using, as the randomness, a hash of the message. Okay. And this means that now that each message encrypts to a single canonical ciphertext. And then kind of to get at the question that was asked earlier, the re-encryption check will also be applied at the same time. Okay? So during the decryption process, when you get a ciphertext, you decrypt to obtain a candidate message M prime, you re-encrypt using the deterministic process, and you check to see if the ciphertexts match. Okay? And this causes, these two things together cause the scheme to become rigid. So ciphertext is only accepted if it is the genuine encryption of what it decrypts to. Okay. So this really restricts the adversary's ability to play around with messages that maybe encrypt to different ciphertexts or vice versa. Okay. Right. And this rigidity is really what makes the chosen ciphertext attack oracle useless to the adversary. Okay. Because we do this re-encryption check on a rigid scheme, we know that we'll only be decrypting honestly formed ciphertexts, and that's what upgrades us to this chosen ciphertext attack security. Okay. And just checking back in on the attacks that motivated this work, right? So when we skipped the re-encryption check, that was what enabled the HQC attack. And kind of this process also enabled the Frodo-Chem attack because that was enabled by the determinism. And the determinism is being introduced here in the T transform as well. Okay. Now, there's another thing that comes out as a consequence of this T transform introducing determinism is that it makes it impossible to achieve the security property we talked about earlier. So determinism costs us indistinguishability. We asked that the encryptions be yield ciphertext. We asked for key encapsulation mechanisms that we have keys that are indistinguishable from random. Okay. And a deterministic scheme can never satisfy that property. That's because the adversary can encrypt things themselves to see if they match the target ciphertext. So if the adversary has to distinguish between, say, the encryption of two messages M0 and M1, they can encrypt both of them using this public deterministic encryption scheme, and they will get what the challenger would encrypt that as. So we break the possibility of getting indistinguishability. The only property we can hope for is a property called one-wayness. So if I give you a ciphertext encrypting an unknown message, can you recover the message? Okay. So we do have the chance of achieving this using a deterministic scheme. All right, so kind of diagrammatically, what we're saying is we started off with something that did have indistinguishability, and we applied this T transform because we wanted to add this rigidity property, but that meant that we lost indistinguishability. Okay? It meant that we got one-way recovery, being hard, but we still want indistinguishability at the end, and so we're going to apply the U transform after this to lift us back up to achieve indistinguishability. Okay, so here's the U transform that does that. So what it's going to do, it's going to be built off of a deterministic public key encryption scheme. So it'll pick a random message, encrypt that message deterministically, and then its task is to output a shared secret, which it will compute by hashing together the random message and the derived ciphertext. And the recipient who's decapsulating can do the same, can do an analogous process here. They decrypt, and this decryption process does include the re-encryption check, and then they hash everything together to compute the shared secret. All right, so all we've done really to kind of lift things up is hash the message and ciphertext together. Why does this give us indistinguishability? Well, if we started off with a scenario where the encryption scheme was secure against message recovery, if it was one way, then the adversary has no chance of learning the entirety of M. If we put this message M, this random message M, into a random function, a random oracle, then the adversary will not be able to compute the output, assuming that the message is sufficiently large. Okay. So with H being a random function, we've lifted from one-way security back up to indistinguishability. All right. Now, there's a couple of subtle details that we should mention about the U transform. We have to figure out what to do in the U transform if the adversary gives us an invalid ciphertext, one for which the re-encryption check fails. Okay? We basically have two options. If the adversary gives us a ciphertext where re-encryption fails and it gives us an error symbol, then we could just output the error symbol, okay, and say, well, you gave us something that failed, we're going to fail. That maybe seems like the obvious thing to do. But actually, it turns out most people choose to do a different thing. They do something called implicit rejection, which is represented by this U with a not perp superscript. Okay? And it says that if the re-encryption check fails, if M prime, the decrypted value, is kind of an error symbol, then we're going to return a pseudo-random value. Okay? Basically, we're going to produce a pseudo-random value by taking the ciphertext and hashing it with a hidden secret. Okay? So this way, on the right-hand side, the decapsulation process always returns something that looks like a key. Okay? Maybe it was a properly formed key. Maybe it was a pseudo-random key that was formed because of rejection, but it always returns something random looking. Okay? And this might hide the fact that rejection is occurring. And perhaps hiding the fact that rejection occurring somehow gives you more security. All right, so this right-hand side is basically what all of the standardized post-quantum chems do today. All right, so just to kind of summarize the kind of overall construction we're working with. So we're trying to go from a public key encryption scheme to a chem, and upgrade the security from passive security to active security. So we start off with a randomized public key encryption scheme. We de-randomize it, and we add this re-encryption check. That gives us something that's deterministic and also has this rigidity property, but at the cost of losing indistinguishability. We only have security against one-way message recovery. So we upgrade it again using the U transform, which turns it from a public key encryption scheme to a chem and restores our indistinguishable security now against chosen ciphertext attacks. All right, so this is the FO transform, and you can prove that this actually works. So the public key encryption scheme satisfies its weaker security property. Then the composed thing satisfies our target strong security property. And you can prove this either in the random oracle model or the quantum random oracle model. Okay. And all of our standardized post-quantum chems use this construction, although each with a slight tweak, either for their own purposes or just because no one could get their act together. Okay. Right. So putting our attacks now in the context of this transform, remember the first attack was against multi-challenge security. So everything I've done so far here only talks about single challenge security. And the second thing, the second attack took advantage of skipping this re-encryption check. And the FO transform here only provides security if this re-encryption check was done properly. So what we're going to try to do in the rest of the talk is see two techniques to address this by changing the FO transform. All right, any questions at this point?
How do they pick the value Z in the implicit reduction?
How do they pick the value Z in the implicit reduction? Yeah, so that'll actually be chosen during the key generation process of the original chem and stored as an extra component in the secret key. Because we need to ensure that when you call the decapsulation oracle with the same invalid ciphertext, you get the same pseudo-random value out each time. So you need to basically keep a secret key for that purpose. But you want it to be separated from your main secret key. So you just append an extra value onto your secret key. Okay. Any other questions? Okay, all right, so let's first talk about multi-target security. All right, so we saw the gap between what we proved, where we had security against one key pair with one challenge ciphertext, and where we might use this, where there might be multiple ciphertexts. In fact, maybe even multiple users with public keys. And the adversary might win by breaking any one of these. Right. So, you can give a generic argument saying that if you have something that's secure in the single instance setting, then it's secure in the multi-instance setting using a hybrid argument. But basically, you get a big factor out front in the success probability, the number of users times the number of ciphertexts. And so this doesn't actually give us meaningful bounds with our parameters. Okay? So we want to try to do better than that. Right, and to remember what happened in the multi-ciphertext attack, so the adversary was given the public key and many challenge ciphertexts, each encrypting random messages MI. And what they did is they sampled their own random messages and encrypted each of those. They stored all the ones that they prepared themselves, and they looked for a match between the ciphertexts. If they found a match between the ciphertexts, then they also know the corresponding message. All right. And we saw that the success probability of this attack was the product of the amount of work done by the adversary times the number of challenges divided by the size of the message space. Okay. All right, so if we look at this bound and we want to try to fix it, well, I mean, we can't change the amount of work done by the adversary or the number of challenge ciphertexts, so the only thing we can try to do is increase the denominator. Okay? So the first thing we can try to do to fix it is increase the size of the message space. Okay? That seems pretty straightforward, except changing the size of the message space might also change other things in the encryption system. So with ProtoChem, it can only handle messages that are exactly 128-bit long with the parameters that are given. If you want bigger messages, you have to make bigger matrices, which will require bigger public keys, bigger ciphertexts, and the scaling is not advantageous. All right, so we have to find some other way to make it work. And what we're going to do for this solution is we're going to try to increase the unpredictability of ciphertexts with a random public salt attached to each encapsulation. Yes?
Sorry, what about HQC?
What about HQC?
Yeah.
So HQC also has salting in it, and I believe it also cannot increase the message space without having a substantial impact on the parameters. But that would be a good question to ask in the HQC reading group next week. That you're presenting at. Okay, great. Okay, right, so how does this salt work? So what's going to happen is, during the encapsulation process, a random message was chosen, but also a random salt value will be chosen. Okay? We'll hash those two together, and that hash together will be the randomness that we use in the de-randomization step. Okay? So we won't have a bigger message, but we will have more unpredictability in the randomness. Okay? Now, the recipient does have to know what this salt is in order to recompute the right thing on their side. So we'll transmit the salt to them in the public alongside the ciphertext. Okay? So it's not extra secret value, but it's still extra randomness. Okay? And then our final shared secret will be the hash, not just of the message in the ciphertext, but also this salt value. Okay? So we can embed this in the two transforms that's part of the FO transform, and call this the salted FO transform. So the main difference here is that, at least during encryption, we sample this random salt, incorporate it into the de-randomization step, and transmit it to the recipient. All right, and this will help us thwart an attacker. Okay? So for the attacker to have a collision that helps them break the scheme, they have to match not only on the message, but now also the salt. Okay? And that salt is going to be randomly chosen. Now, if they try to do a bunch of pre-computation in advance, they're not going to be able to predict the salt that's used in all of the challenges with very good probability. Alternatively, they could wait for till they see the salts in all of the challenges out there, but because each challenge is likely to use a different salt with high probability, then they can't really do batch attacks. They can only pick one particular instance and target that, the instance with that salt. Okay. So our probability of successful attack now gets this nice extra factor in the denominator, and if we have sufficiently big salts, but not really big actually, like 32 bytes is enough here, then the success probability in this multi-collision attack becomes negligible. Right. Okay, so this would solve our problem. It actually solves another attack problem, which none of you complained about, and I'm very disappointed about that. There is an attack even without the adversary doing much work at all. Okay? So among these challenge ciphertexts in our multi-challenge attack scenario, it might be that some of the randomly generated challenges happen to collide with each other. If the message space is not too big, then there will be some probability that the challenger picks the same message and issues challenges for both of them, right? And the probability of such a collision will be roughly the number of challenges squared over the size of the message space. Okay. And this also leads to a distinguishing attack in our game, because if you see two ciphertexts, they should correspond to the same message and thus lead to the same encryption key. But if we are doing our attack scenario where you get random keys, you get two, with high probability different, random keys for these two identical challenge ciphertexts, and that would let you distinguish. So the adversary doesn't even have to do their own work in forming challenges. They can just look for collisions among the challenges that they were given. Right. Right. And salting happens to reduce this type of collision as well. So this salting actually solves two things at once. Right. So we can give some provable security results for this salted FO transform. It's kind of, well, the bound here, but basically says if you have something that is secure against chosen plaintext attacks, it is secure against chosen ciphertext attacks up to these additional factors here. And because we have the salt now appearing in this denominator here, we can keep the bounds nice and small. And we also have results against quantum attackers. All of the quantum results are non-typed. Okay. So this really does give us an improvement compared to where we were before. So this was the bound for the unsalted version of the FO transform, and we can make that go to about 1 for the Photochem protocol, but the salted version we can keep negligible. Okay. Right. And so this really does recover the multi-challenge security that we might want. Okay? And it does so with a fairly minimal overhead. So 32 bytes of communication and less than 1% extra computation. And so this tweak is included in the version of Frodo that was standardized by the International Standards Organization. All right. Let me briefly mention the second line of work on verifiable decapsulation. Okay, so we noted that the second attack came about because the re-encryption check in this algorithm was skipped. Okay? And it went unnoticed for a long period of time because skipping it didn't actually render any failures in the test suite. Okay? All of the honest ciphertext still successfully decrypted, so all of our tests still passed, and security was gone. Right. And so this is actually an example of a concern that was raised a few years before this occurred by Nadia Henninger, and then in a paper by Mark Fischl and Felix Gunther, where they talked about tying security to functionality. Okay? So if you have a security critical step, you want to make sure that the scheme won't work properly if that security critical step is skipped. So an implementation that's faulty, not faulty because an adversary messed around with it to try to trick you, but just because you were incompetent. If you have that kind of faulty implementation, that should hopefully break something in a visible way so that you know you have to fix something. Right. So Fischl and Gunther formalized this in an idea called verifiable verification. Okay? So we want to modify the scheme somehow so that its output changes visibly if some security critical step is skipped. Okay. And they're going to do this by having algorithms produce additional outputs called confirmation codes. Okay. So this confirmation code will be some kind of extra output produced by the algorithm that's unpredictable if you skip certain steps. Okay. If you skip the step, then you probably won't be able to produce the right code, and then maybe something later will happen that depends on that code. You can formalize this. They have a notion called confirmation code unpredictability. And so we don't need that the unpredictability of these confirmation codes be too high. Okay? So normally in cryptography, we look for things to have distinguishing advantage at most 2 to the negative 128. Really, really tiny probabilities. But here, we're not thinking about a malicious adversary, just an incompetent programmer. Or a complement. So we don't really need things to be hard to fool with very high probability. If this thing fails half the time, that's still good enough, because you're going to notice if your test suite fails half the time. All right. So we can find these confirmation codes in existing public key encryption schemes or existing chems. So for example, MLChem, the standard from NIST, its ciphertext are compressed versions of polynomials. Polynomials whose coefficients are integers mod 3329 of degree 256. The way compression works is it basically rounds these coefficients from being integers mod 3329 to integers mod, say, 1024. Okay. It's kind of like dropping all the low order bits and only keeping a few all high order bits, although it's rounding, so it's slightly different. But this suffices for our purposes. Okay. And it turns out that these discarded bits that were dropped can basically be used as an unpredictable confirmation code. So this remainder will be unpredictable if you don't redo most of the encryption computation. Okay. And during the normal decryption computation, you are going to go through and recompute all of these in order to know what the corresponding higher order bits are. So this is a good candidate for a confirmation code. It's going to be naturally recomputed during re-encryption, and it's unpredictable if you don't follow all the steps. Yeah. All right, so we're going to wire that into the Fujisaki-Okamoto transform. So we'll have our base public key encryption scheme output a confirmation code that would be hard to predict unless you followed the process correctly. Okay. We'll pass that along through the T-transform, and then we'll bind that confirmation code into the resulting key. So we'll just hash it alongside the message in the ciphertext. If you don't get the right confirmation code, then the hash will likely result in a different key K coming out at the end. All right. You don't have to transmit the code. In fact, you shouldn't transmit the code because we want the recipient to have to recompute it in order to get things correct. All right. This overall composition still gives us our desired security level, chosen ciphertext attack security, But it also kind of results in this new property where a faulty implementation now yields a wrong key. And we have a kind of a security notion capturing this called faulty correctness. All right, so I'll skip the formalization of that. But I'll note that when we apply it to two of the standardized schemes, it's pretty straightforward to do. I already told you how to do it for MLChem by looking at these bits that were dropped during compression. And if you do that, you get confirmation codes that are guessable with probabilities in this range, depending on how you count. But it's still going to be noticeable in tests, and with very little computational overhead. And for HQC, they also have kind of compressed ciphertext where you just drop off portions of it. And again, we can use that, which adds very little overhead and is quite unpredictable. And if we had used this in the original HQC implementation, then we would have detected the bug immediately rather than 19 months later. Right? And so we proposed to NIST that this should be included in the final spec for HQC. Although it's too late to do this for MLChem, it's already standardized. Right. Now, one drawback of this technique is that it does modify the scheme. Okay? So hashing the code into the key right at the end changes how the scheme works. Okay? And maybe that's okay to some people, but if you're obliged to follow standards, then that might be unsatisfactory. Okay? And so in the last bit of work, we came up with a way to do that where we don't have to change the computations in the base scheme. We do have to pull out an intermediate value during that computation, but we can post-process it afterwards in something like a wrapper that builds around it rather than modifying the core scheme. And the hope would be that that's a little bit more desirable to people who have standardized implementations already. Right. Okay, but I think I'm going to skip the details on that and just jump to the end and wrap up. Okay, so kind of we saw two themes in the talk. The first theme was around the multi-target gap, okay, where we had a security definition that was the original target security definition, single ciphertext security, but that didn't match deployment. Okay. And so our approach there was to incorporate this unpredictability, assault. And on the second theme, we saw implementations could have flaws. And our approach to detect these flaws was to make security critical steps observable because skipping them changes the output. All right, and the kind of common approach for addressing these was to modify this Fujisaki-Okamoto transform. Right? So in one of them, we added assault, and that got us multi-target security. And the other, we added a confirmation code to tie security to functionality. Okay? And found an extension where we didn't have to modify the internals of the algorithm to preserve standards compliant implementations. And both of these have already had some impact. The first version is included, the salted version is included in the photochem standard, and we've talked to NIST about the second one for them to include before standardization is finished. Right. A few open questions that follow from this. We don't have tight QROM bounds, tight bounds against quantum random oracle model adversaries for the salted FO transform. We don't know if these salt bounds are optimal. Let's see. And there's kind of re-encryption is kind of a really interesting question overall. Do we really have to do re-encryption in order to achieve this level of security against active attackers? It seems kind of hard to avoid, but it would be really interesting if you could. All right, so I'll wrap up there, and happy to try to answer any questions you might have.
Thank you, Douglas. Any questions? Please wait for the microphone. I definitely have some. So it also seems like we could have avoided the second confirmation code bug by just having a test suite that has a couple bad ciphertexts that must return an error. And it seems like that actually can be added to the standard already without modifying the standard and would have solved it in sort of a software engineering level rather than a protocol.
Right, okay, so So could we add ciphertext to the test suite that must return an error? Remember, this is the implicitly rejecting version, though. So they don't return an explicit error code. Instead, they return a pseudorandom value. So how do you tell that that pseudorandom value corresponds to an error? I guess you could undo that partially and know that it was see partway through the computation that it would have returned an error if we didn't have the wrapping at the end that re-randomized, that added the pseudo-random version. I don't know why someone wouldn't have done that, but it was not done.
Yeah.
Yeah.
I have a kind of sociological question. My question is just about the way that standardization has gone for the post-quantum crypto in general. I mean, it seems like ideally, like this discussion would have been had, before the process was coming to an end, or has come to an end. What's your view on how this post-quantum crypto standardization has unfolded over the past few years?
Right. So this is my first time involved in a big algorithm standardization process. Did it go the way it should, or could it be improved? And I certainly think some things could be improved. So you start off with many, many targets that the research community has to analyze. And they do try to narrow them down, but it kind of takes time to understand how they're going to be used. And then even kind of things that seem like aren't the core cryptography still come up and be important. So a lot of work in the first round would have been just focusing on the core problems. Do we believe that the module learning with errors problem is hard? Have they tuned the parameters to the right security level? I don't think people would have been looking for some of these more esoteric problems. So I think part of it is just that we weren't looking, or we didn't have the capacity, but also we didn't know to look for these types of problems, right? So the multi-ciphertext attacks, we didn't really think about that too much beforehand, at least as far as I know. No one was really thinking about these beforehand. There's a little bit of thought about multi-user hardening, but this was all done in a very ad hoc way. So people hashed in the public key to try to prevent multi-user batch attacks, but no one formalized it. No one wrote down a definition and said, oh, this provably achieves that until 2023, I think.
Thanks.
Yeah. Mustafa?
I have a basic question. We know that sometimes we need to encrypt a message that is large. So we compute its hash value, and after that encrypt it. What about, you said that we cannot increase, if we increase the size of message space, the computational cost increases. What about the case that, probably I'm wrong, but what about the case that we first hash the message space or a message, and after that turn it into 128 bits, and after that?
Right, okay, so I think the question is, if we can increase the message space here, can we do something else? So if we go back to this point here, so for example, could we start with a bigger message originally and then hash it down and work with that? So basically you have to focus on the narrowest point in the entire system. So even if you start off with a larger value and then eventually hash it, it will be the narrowest value where the adversary could target to try to find a collision. And this actually caught us up when we were trying to patch Photochem. We originally did one patch and we thought it fixed it, and we saw that there's another choke point where it was narrow at another point, and we'd missed that, so we actually had to move where we incorporated the salt to make sure we covered all the narrow choke points.
Right. Thank you.
About this salted Fujisaki-Okamoto transform, I was thinking about it throughout the talk, and it seems, at least the first part, contradictory to the fact that the original one, the T-transform, you de-randomize the public key encryption, whereas in here, you do randomize. You have this additional salt which serves as your randomness. Is there some sort of contradiction to these 2 points, or am I thinking about it the wrong way? Or maybe more specifically, what's the difference between doing what you've done here compared to just choosing something at random and classifying that as your salt?
Right. That's a good question. I think philosophically, I mean, so I guess we are reintroducing some randomness in this de-randomized step. I don't know if that's philosophically a problem. So I'd have to think about that more, actually. Yeah, let me think about that.
Sure.
Okay. Sorry.
I think we're at time.
I'm happy to chat afterwards.
All right. So let's thank Douglas again.
Thanks.